Welcome back, dear students, to the tetrahedron chemistry classes. So in the combined spectral problems, today I am going to solve yet another problem from the book Spectroscopy by Pavia, Lampman and Crace. This is the problem number 12 from the chapter Combined Spectral Problems, and this question was actually asked by one of my subscriber who was struggling to solve or to get the correct answer for this particular question. So today I am here with the solution of this particular question. What is the question? Determine the structures of the isomeric compounds A and B. You have been given two isomeric compounds A and B, each of which has the formula C8H7BRO, which I have written over there as well. The IR spectrum of compound A has a strong absorption band at 1698 centimeter inverse, while compound B has a strong band at 1688 centimeter inverse. The proton NMR spectrum for compound A is shown along with the expansions for the region from 7.7 to 7.2 ppm, and the expansion is on the next page, and the NMR spectrum of the compound B is also attached, which is on the third page. Okay, so I'll solve this problem according to my usual way. First of all, we'll calculate the hydrogen deficiency index, and it is for the beginners. However, it is clearly given here. You are getting a signal here at 7 ppm. It clearly indicates the presence of the benzene ring. Okay, and along with this kind of the multiplate, you are having only one peak. So spectrum is looking quite simple, but its expansion, the expansion of this particular region will give you the more insight about the structure. Okay, but as my usual way, first of all, I will calculate my hydrogen deficiency index. So here the formula is 2C plus 2 plus N minus H minus X over 2, where C is the number of the carbon atoms, so 2 times 8, right, and then plus 2, and then plus 0 because no nitrogen is present here, minus 7, which are the hydrogens, and then the minus 1 divided by 2. Minus 1 is for your one of the halogens which is present here, and if you solve this value, then you will have this hydrogen deficiency index of 5, and this 5 basically indicates the combinations of the rings and the double bonds. Since I am having my proton NMR spectrum, which is giving a signal at 7 ppm, so one thing is clear, my molecule is having this particular benzene ring, right? So this benzene ring basically fits in the hydrogen deficiency index of 4 because 3 double bond and 1 ring is there. Okay, and now you left with the fifth hydrogen deficiency index, and of course it is basically your carbonyl group. So in this particular question, in the little while you will find that IR information which we'll get from the information which we are having from the IR spectrum is more important to solve this particular question. Okay, so first of all, it is showing two very strong absorption. Strong absorption means your polar group is present, and that polar group is the carbonyl group. Okay, and in the compound A, it is resonating at 1698 centimeter inverse, and in the compound B, it is resonating at 1688 centimeter inverse. That means little bit of lower frequency is there. That means to stretch this carbonyl bond, we will require the little bit lower energy for this particular compound B when compared to the compound A, because it is having this 1698 centimeter inverse of this frequency, which is corresponding to the little bit of higher energy, right? So and then you are having this carbonyl group, and bromine is already there. So we can quickly discard the possibilities of having acids, because acids are having two oxygens which are not there in the question. Similarly, you can discard the possibility of the esters as well, okay, and other acid derivatives. So the only possibility you left with is the presence of the carbonyl group, either in the form of the ketone or in the form of the aldehyde. But aldehydic possibility we can safely discard, because you know your aldehyde proton resonates between 9 to 10 ppm. That means if this carbonyl group is of your aldehydic carbonyl group, then you must have a signal between 9 to 10 ppm in the proton NMR spectrum, which is absent here. So that means this compound is not aldehyde, it is simply a ketone, right? And you are having this singlet Singlet, you know how we can get the singlet. Singlet we can get by this CH3. Okay. So, and these three fragments we have already identified. Now, last is your Br. So, basically, these are the four things which you need to put together in order to get the correct structure for this proton NMR spectrum. Okay. So, it's simply the acetophenone type of the compound in which your bromine is substituted. Okay. And when you substitute bromine on the acetophenone, it may be your ortho substitution, it may be your meta substitution, it may be your para substitution. Okay. But before going further, you need to check this particular expansion which is given on the next page. Okay. So this is the complete expansion, and it is very important for the students to know or to identify the pattern given in the expansion for the particular compound, right, in the proton NMR spectrum. So what I am observing here, it is very important thing. See, I am having one peak is here. This is one peak. Okay. I am writing one peak. Okay. And my second peak is this one. So this is your second peak. And my third peak is this one. So I am writing this is as third peak. And the last one is my fourth peak. That means in the proton NMR spectrum, you are getting four peak for benzene. Why benzene? Because it is the expansion of the benzene region, which is extending from 7.24 ppm to 7.64 ppm. So you can say how I am counting the only four peaks. However, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 peaks are there. No, they are not 11 peaks. They are the complex splitting pattern of the four peaks. When your benzene molecule is having four peaks, that means you are having the four different hydrogens. So how we can get the four different hydrogens? You have this benzene and say your carbonyl group is here, CH3, and I'm substituting my Br here. Okay, this is the one possibility. This is your ortho-bromo-acetophenone. So if you write this ortho isomer, then you will have this hydrogen, and you will have this hydrogen again, and you will have this hydrogen again, you will have this hydrogen again. And for all of four, these hydrogens are different. So all these will show different peaks in the proton NMR spectrum in the region between 7.1 to 7.5 ppm or 7.7 ppm. Okay. So this is basically, say, this is peak 1, this is peak 2, this is peak 3, this is peak 4. Okay. Now, or I can mark these hydrogens as a different hydrogens. Say for example, this is your, say, principal functional group. This is carbon 1, this is carbon 2, this is carbon 3, carbon 4, carbon 5, and carbon 6. Okay. So I'm calling this hydrogen as the hydrogen 3. Okay. And this hydrogen as a hydrogen 4, this as hydrogen 5, and this as hydrogen 6. Now you can see here the environment of this particular hydrogen 3 is the bromine on the right hand side, while on the left hand side the environment of this hydrogen is hydrogen, only hydrogen. Okay. So this hydrogen is basically different from this particular hydrogen because the environment of this hydrogen is H5 and H3. So these two are different. Similarly, if you see this hydrogen, meta to this hydrogen, at the meta position to this hydrogen is carbonyl group, while meta to this hydrogen is this Br group. That means this is also different from this one. That's why I have marked this hydrogen as the different hydrogen as H5. Similarly, this hydrogen in the ortho position is having your acetone functionality, while this hydrogen is having the Br functionality. So all these hydrogens are different kind of the hydrogens. When they are the different types of the hydrogen, they will produce different peaks in the NMR spectrum. So you will get the 5 peaks in the proton NMR spectrum. Okay. Now, if you see the pattern, this pattern is known as the DD pattern. DD means doublet of doublet. So this is one doublet, this is yet another doublet, this is known as the doublet of doublet. Okay. And then this one is also your DD, doublet and doublet pattern. But here you can see 1, 2, 3. 3 peaks are clustering at the same value, right? So this is known as basically TD, triplet of doublet. That means doublet 3 times, 1, 2, 3, and all are the doublets, so it is TD. And the last one is also here TD, which is known as the triplet of doublet. Now the question comes, why we are getting the triplets of the doublet? So if you want to explain this doublet and doublet of doublet and then this triplet of doublet, so how we can explain? See this H3, okay, this H3 will couple with this H4, so it will produce a doublet, and then again it will couple with this one, so it will again produce a doublet. So the doublet of doublet, which I have shown here. But this H4 is forming a triplet of the doublet. Why? Because this hydrogen will couple with this hydrogen, producing one doublet, and then this will couple with this one, it will produce another doublet. So two doublets are there, and then this H4 will couple with this hydrogen as well, meta coupling, so another doublet, so three doublets. And then you are having this hydrogen, so one doublet will be produced by this H6, another doublet will be produced by H4, and another doublet will be produced by the H3. So ortho and meta both couplings are there, so this will also produce triplet of the doublet. So these two, H4 and H5, will produce a triplet of the doublet, while this will produce only doublet of doublet. So it is quite simple here, you can see. So basically your compound is looking like that it is orthobromoacetophenone, CH3. They will produce only one singlet. Okay, so if you want, then you can very simply write this is giving your TD, this is also giving your TD, and this is giving you DD, doublet of doublet, right? Now the question comes, what if we have this particular isomer? So this is also having the different hydrogens. This is H, this is second H, this is third H, this is fourth H, and they all are different. Say HA, HB, HC, HD. This can also produce the similar NMR pattern which is given in the question, and I'm saying that this is correlating with this orthoisomer. Why it is not correlating with this one? The answer comes from the IR spectroscopy, right? IR spectroscopy in this case is very important in order to decide the structure. So what will happen, you see, in the question itself it is given that for this particular compound the value of your IR stretching frequency is 1698 centimeter inverse for your carbonyl. Why this happens? You see, this Br and this COCH3, they are at the ortho positions to each other. What will happen? This bromine will create steric repulsion to this carbonyl group, and due to this steric repulsion, this carbonyl group will no longer remain in the plane of the benzene ring. So the very smooth resonance overlap would not be there for this carbonyl to this benzene ring, because it is out of the plane due to the steric repulsion. It will be pushed, this carbonyl group will be pushed outside of the plane of the benzene ring, and there is no very smooth overlap. And you know, the conjugation lowers the stretching frequency in the IR spectrum. But here in this case, that conjugation is not very smooth. This will require little bit of high energy to stretch this carbonyl bond, which will reflect in the higher value of your carbonyl stretching frequency 1698. While in case of the meta isomer, this carbonyl group will remain in the plane of the benzene ring. So there is a very smooth conjugation, extended conjugation between this carbonyl and the benzene ring, and this value will not be very high like in the earlier case in the orthoisomers 1698. It will be somewhere around your 1988 centimeter inverse. That's why I am saying that this particular compound A, the isomer A, is basically your this particular compound, which is your orthobromoacetophenone. This thing is very important for you. Okay, now if you go back, you see here, this is the cluster, and the expansion of the cluster I have explained to you. Then you are having this one singlet, and that one singlet is due to this CH3. This is how I am confirming that this compound is basically your orthobromoacetophenone. Now if you move further. Say this is your compound B. So what is there in the compound B? You are having one singlet, of course this is for CH3, and then you are having only two doublets. You are having only two doublets. That means it's simply saying that you are having two sets of the hydrogen. One set of hydrogen, and this is second set of hydrogen. Only two sets of hydrogens are there. That means out of four hydrogens, two forming one group and other two forming two groups. And this will happen only in case of this isomer, right? Say for example, this is your benzene ring and this is your COCH3, and at the para position you are having this Br. Okay, now you see this molecule is having the plane of symmetry, which is bisecting this benzene ring from this carbon Br bond to the carbon carbonyl bond. So if I try to put this, so this is the, you see this is the plane of symmetry which is going in that manner. So when plane of symmetry is here, that means this particular hydrogen, which I am calling as Ha, is identical to this hydrogen, which is your Ha. Similarly, this hydrogen we can mark as Hb, and this is also Hb. So due to this plane of symmetry, these two hydrogens are equivalent. These two hydrogens are equivalent. Okay. So equivalent hydrogens do not split each other, but this Ha will be split by the Hb. Only one hydrogen is there, so this will produce a doublet. One doublet for this Ha set. So I am writing here. Similarly, another doublet. Okay, that's why only two peaks are here, and one peak is for this particular one. So second isomer is basically your para isomer. In this para isomer, there is a very smooth conjugation between the electrons of the benzene rings and this carbonyl group. So lesser energy will require to stretch this particular bond, which will reflect in its lower value in 1688 centimeter inverse. So basically these two isomers belong to the two different kinds of the acetophenones. One is ortho derivative and second is the para derivative. So there is no possibility of meta isomer in this case. Okay.